So first example is a situation where we're given the equation of which models a particular situation, and we use that to find some maximums or minimums or something like that. The second example is a situation where we're not actually given the equation, we need to obtain that equation somehow. Okay, so first example here, population of a colony of birds at any time where t is the number of months after observation began. It can be modelled by the function there, which is a sort of a kind of like an exponential, but it's actually a combination. You can see here that the p of t is by going 400t times e to the negative t over 5 plus 600. P is the number of birds. So the initial population, to find that, okay, that's not really a calculus problem, that's just saying, okay, what is the initial population? Well, we need to let t equal 0. So in other words, what was the number of birds when the observation began? So p of 0, you can see, is going to be 600, because when we replace t with 0, it eliminates that first term. So that's the initial population. The second part, when the largest number of birds is reached, the key word there is the largest number, okay? So you need to be thinking, okay, we're dealing with a calculus problem here. Maximum corresponds to a maximum, like a maximum turning point, if we just had it as a graph. Okay, so we're going to think, okay, maximum, that's a stationary point. Okay, so we want to find whereabouts the stationary points are. So we need to find p dash of t, and we would use, in this case, the product rule, because it's 400t times e to the negative t over 5. So we need to use the product rule for that. So if we've got u equaling 400t, then u dash would be 400, v would be e to negative t over 5, so v dash would be negative 1 over 5 e to negative t over 5. And of course the plus 600 will differentiate to the value of 0, so don't need to worry about that. We could take out a common factor there of 400 e to the negative t over 5, leaving us with 1 minus 1 over 5t. So that's our derivative. And quite honestly, if this section was in the calculator section of the exam, there's no reason why you couldn't find your derivative using the calculator, which would be useful if you wanted to use the second derivative to confirm it being a maximum or a minimum value. Okay, so that's perfectly fine. I mean, if you're dealing with just a basic polynomial, finding a second derivative is straightforward manually. When you're finding the second derivative for something like this, it just becomes increasingly a little more complex, okay, with this type of problem. And in which case, I'd probably lean towards using the gradient table to confirm a maximum or a minimum if I wasn't using my calculator. Okay, just for speed, basically, to work through things quickly. Okay, so that's our derivative. Now, stationary points, because we want to find the maximum number, well, when the largest number of birds is reached, so when is the maximum corresponding to a stationary point, we want to find the stationary points, okay, and that'll be when p dash of t equals 0. So that means we've got 400 e to the negative t over 5 times 1 minus 1 over 5 t equals 0. And that's where it is useful to have it factorized like this, okay, because we can just use our null factor law. Okay, so in other words, 400 e to the negative t over 5 equals 0, or 1 minus 1 over 5 t equals 0. With our exponential there, there's going to be no solution for that one because that exponential can't equal 0. Okay, so which means we're just left with t would equal 5 when we solve for t. So when the largest number of birds is reached, well, it looks like it'll be 5, but what we need to make sure we're doing is we're just confirming that actually that is going to be a maximum and not a minimum or a stationary point of inflection. So you would then just, probably in this case, we'll just stick with using our first derivative gradient table. So we can just choose a value of 4, 5, 6 point either side of 5. And now it's 0 there. And if we substitute in a value of 4, okay, so that first part there, that e to the negative t over 5 times 400, that's going to be positive. But when t equals 4, then we've got 1 minus 4/5, which is a positive value. So that's positive. When t is 6, that'll become negative, and so we can see that it is going to be, in fact, a maximum value. And for part C then, we want to find the actual maximum number of birds. We're going to put t equals 5 into our original equation. I think from memory, I've got it in front of me, it's about 1,336 birds, the maximum number. All right, next example, okay, we have not got the formula, but we can work it out if we know the formula for 1, the surface area of a cylinder, and 2, the volume of a cylinder. Anyone remember what the formula for the surface area of a cylinder would be? Yep. Yeah. Okay, so we've got the 2n, because it's a closed cylindrical tin can. You've got 2 pi r squareds, the 2 n's, and of course the circumference of the circle multiplied by the height, so 2 pi r times h. So our surface area, 2 pi r squared plus 2 pi r h. Volume of a cylinder. Yeah, that's right. Because the area of the base times the height. Okay, so there's our formula. Now, in the exams, pretty much most of the time they actually give you the formulas, which is probably good for some who can't remember how to work some of these out. But that's okay. The key really is not how well can you remember area and volume formulas, but how can you apply calculus, and so that's why they tend to give it to you. Okay, so we need to be able to look at this question. It's saying we've got a particular value for the surface area, so that's obviously going to be useful somehow, but what we're ultimately trying to find is the greatest volume. Okay, so we want to maximize the volume, so somehow using calculus, we've got to think, okay, we need to know our volume formula and we need to find where it's a maximum. Okay, there might be some situations where things are a minimum or a maximum. So again, we're thinking in terms of calculus, we've got to think stationary points. Okay, so we ultimately need our volume formula. The issue here is that our volume formula is in terms of two variables, radius and height. We can't differentiate volume with respect to two variables. We can only do it with respect to one variable. So we need to eliminate the height or radius or something like that, so that we've just got it in terms of, say, the radius only. Okay, and that's exactly why we have the information about the surface area. Okay, we know that 2 pi r squared plus 2 pi r h is equal to 100 in this situation. And so it's definitely going to be easier if we rearrange that and make h the subject, because we've just got the one term with h in it, as opposed to r, which has got r and r squared. So rearranging to solve for h. Okay, so we'll have 2 pi rh is equal to 100 minus 2 pi r squared, and then we can divide by 2 pi r. So h will equal 100 minus 2 pi r squared over 2 pi r. And that's okay to leave it like that. What that means now is that we have an expression for the height in terms of r, which can go into our volume equation. Okay, so volume being pi r squared h now can be written as pi r squared times 100 minus 2 pi r squared over 2 pi r. That's replacing our height. And we can see that we can cancel our pi and one of our r's there. And so we're going to be left with 100 r minus 2 pi r cubed over 2, which will be a little bit easier if we make that 50 r minus pi r cubed. Okay, so we have now our volume formula for this particular cylinder, okay, just in terms of r. So that's where we needed to get to before we could actually apply any calculus. So now what we can do is differentiate our volume equation with respect to r. So dV dr will be 50 minus 3 pi r squared. Okay, so solving for r, we can see we've got the square root of 50 over 3 pi. There's very little point in doing minus, like a plus or minus there, because a negative radius is not going to be very relevant. So we've got square root of 50 over 3 pi, and again, we need to just confirm that it's a maximum. So what we can do is differentiate again. Now in this situation, okay, it's a really straightforward formula. So we could find d2v dr squared and say, well, that's going to be negative 6 pi r. Okay, no matter your radius, your second derivative here is going to be negative. So d2v dr squared is negative for all r values. And the positive, okay, which they will be. Which means that volume is a maximum for being equal to the square root of 50 over 3 pi. Okay, so that's an example of a nice sort of straightforward application of using our second derivative to confirm the nature of the stationary point. Okay. Now we've got our, we need to actually find the volume, so we're just going to substitute that in. So there is 50 times 50 over 3 pi minus pi times the square root of 50 over 3 pi cubed. Definitely going to need a calculator on that one. Okay, as an exact value, that happens to be 500 root 6 over 9 root pi. Doesn't really make a lot of sense, does it? So, but actually, two decimal places, which it asks for, is 76.78. What's that? Yeah. Okay. So cubic centimetres. So that is our maximum volume. Oh, did that just go off then? Right. Okay.
Oh, it's just the textbook.
Oh, yeah, okay, gotcha. Thanks. Right, actually, I don't know where I can do here. Go back. Oh, there we go. Sorry to disappoint you. All right. Now, actually going to go to the yellow book and work through exercise 8H. Yeah, this one. Sorry about that.